The first presentation is about the resource management and how we should manage the resources. So we will introduce the concept of ownership. We will see how the row pointers and smart pointers are useful, and we will end with some guidelines about how to use them and when to use them, and also how to pass parameters in our code. So C++ is an object-oriented programming language, and let's say its main selling points are performances and letting the user have full control over the resources. Performance and full control are somehow faces of the same coin, because full control allows to do very clever and smart things to get best performances, and in HPC performances are one of the main target, if not the more important one. But with greater power comes great responsibility, because yes, we have full control, we can do whatever we want, but we have to do it correctly. Let's start talking about what a resource can be, what we have to deal with. A resource can be the memory, which is the most common one, memory allocation. But a resource can also be a mutex, maybe while programming in multi-threaded environments. And but it could also be an MPI communicator. So if you ever have to deal with MPI, you know that a communicator may require some initialization and releasing procedures. So having full control of them means managing correctly them. So you have to initialize or acquire it. You have to keep it alive for the entire duration of the program, or at least when you have to keep it alive until you need it, because you don't want to keep alive a thing that you don't use it anymore, because it is a waste of resources. And at the end, you have to release it cleanly, because you don't want to have to keep alive things that you don't use anymore. Why should we care about managing correctly the resources? Because we can even think, well, when my program finish, all the resources will be released. It's not always true, because we may have to deal with resources managed by other libraries, and that may have to connect with the operating system. So we have to cleanly manage the resources, because a not managed resource may end up with subtle bugs, really difficult to find out. And this is the best case, because maybe a memory leak is not the worst nightmare, but if you ever had to work with multi-threaded environments, you know that the race condition is very, very hard to deal with and to find out the reason. And not managing correctly a resource easily may end up in a race condition. But managing the lifetime of a resource in an object-oriented context is really difficult, because the object gets created, manipulated, you can pass around the things, and it's not so easy to keep track of things. And it is also not so smart to think about, well, I'll keep track of everything by myself. It's quite hard. And as soon the program complexity starts increasing, it becomes unsustainable and also impossible in some context. But full control doesn't mean you have to do it manually, because the language through the compiler is at our disposal. It is not there just to impose us some constraints. We can use the constraints imposed by a compiler and the language to be leveraged at our service. And in this presentation, we are going to see what we can use from the language and we should use and rely on to keep things under control. Because our target is writing, yes, efficient code, but it has to be maintainable, readable, and correct. Let's start from the very basics. Let's see on the left, there is a toy example of an object. And we have few handles on the object to control his life. We can see the constructors and destructors, and they can be used to define the semantic of the management of the resource. So what we have to do to create a resource, to allocate a resource, to acquire a resource, and to destroy, release a resource. And this is what has been already presented by Mauro, I think yesterday, with the RAI technique, which allows you to define what you have to do when you acquire a resource. So we can write it in the constructor, what we have to do when the resource has to be released. So we are going to implement the destructor, and the constraints of the language makes this thing work because the constraints on the object's lifetime becomes constraints of the resource lifetime. Then we have also copy and move constructors with related assignment operators. And they define what happens when the object is, let's say, passed around. With copy, it is a bit tricky because it may have a different meaning from object to object. I put a note down there because an object may have a value semantic or reference semantic. I won't go very deep in this, but just to get an idea, a copy for an object may mean cloning an object, so creating a clone which is completely independent from the one that from which you call the copy. But it can also mean just sharing the same resource. And so it depends on the semantic. While for the move constructor, it should be more straightforward to think, because today Mauro presented the move constructor, no, yesterday presented the move semantic. And with the move semantic, we steal the inside of an object from another one. Here in this slide, I highlighted the RAI technique and the ownership word, because the RAI technique, one of the fundamental concepts that on which it is based, which introduced, is the ownership. The ownership of a resource. In fact, with RAI, an object starts representing the ownership of the resource. So it has the responsibility of the correct management. But having the ownership of the resource means that we can think of the object itself as the resource. So we can deal with the object instead of thinking, I have to release the resource, I have to manage the resource directly. So the developer does not have anymore the direct responsibility of the resource, but it does not mean they don't have anymore the control over it, because we delegate the hard work of managing correctly the resource to the object. And we can now start reasoning about the ownership. And this is really useful and helpful because it's a higher level of control. It's more, let's say, abstract in some way, because we don't care anymore about what happens when the resource has to be created and released. We define it in the object implementation. We just have to think where and how long we need the resource and manipulate the object accordingly. So we can think of the object as a representative of the ownership, and we can assign the ownership of the object to different parts of our code. So when the different parts of the code, being threads, other function, whatever happens in our code, when we pass the object, we know that we are passing the ownership of the object. About the ownership, we can differentiate two main types of ownership. The unique or exclusive ownership. This is when there is exactly one object instance managing a specific resource. So we are sure that no one else will have to deal with the resource. Just one will deal with the ownership. And then we have the shared ownership, where there are more objects managing the same resource. For the first one, the unique or exclusive ownership, it doesn't mean that we can access the resource just from one specific point of the code. We can move around the ownership, but we are sure that just one point in the code will have the ownership of the resource. While with the shared one, we can have multiple threads sharing the same resource, exactly the same resource. The first one can be implemented using mainly just the language, in the sense that we will see an example in a few minutes. While the shared ownership requires a machinery, because the language itself is not enough. But we will see an example quickly. Let's talk about a use case where we can understand a bit how the ownership concept applies to our code. And we will see the use case with pointers. I'm pretty sure that everyone already had to deal with raw pointers with C or C++. But pointers are not the right thing to use for managing resources. Let's see the small snippet of code that is on this slide. The same pointer, let's say, we can define the pointer at the same way, but to it we can assign a single value allocated on the heap, multiple values, an array of values allocated on the heap, but we can also store in the same exact pointer also a reference, a point. It can be a pointer to a value on the stack. And if you look just at the left part where we declare the pointer, just the name that we used gives an hint about what we allocate, what we do on the right. But the type is always the same. So let's see what the problems are with managing resources about pointers. If we get let's say, a library, which gives us this function, this signature, and this function says that, well, it takes in some parameters, one of which it is a pointer, and it returns a pointer to a GSL multi-fit fsolver. Who is responsible of the return pointer? Because behind that pointer, we may have a value on the stack, a value on the heap, and this, if it is not a value on the stack, it has to be released in case it is allocated on the heap. So who is responsible of doing that? The library? Maybe we have to call another function, or we are supposed to release it and as soon as we don't use it anymore. Well, this is one big problem because the API is not so clear about the contract that it established with the user. But we will see more later. Okay, now let's say that the library, the previous function, gives us the responsibility of the right management of the returned pointer. How we know how it was allocated? Because if it was allocated with new, we have to call delete because they are paired. If it was an array, we have to use the delete array. And if the library used malloc, we have to use free. So there is another point of, it's ambiguous because we don't know. We should look at the documentation. We should know how the library works. Okay, let's say that we also know how we have to deal with that, but we have the burden of the management. And well, we have to remember to do it. And it is not trivial because, well, we have to do it mainly, maybe for a lot of resources, maybe for different resources. And we have to do it in the correct order, because if there are dependencies between resources, it becomes even more difficult to do it correctly. Let's say we are the perfect programmer that can keep track of all these things. Have you considered all execution paths? Because if a function has multiple return statements, you may have to care about it multiple times. Because if we have an early return in a function, and in that function we have to release to delete a memory allocated, we have to do it before the return statement. And if there are more, it may be not so straightforward to do it, and the code may become less readable. And even if you consider all the execution paths, there may be also exceptions. In case of an exception not managed, it becomes impossible to manage correctly, because we don't know when it is raised, and so it can happen at every point in the code, and so we don't know when we should release the exception because we are doing manually. And so we can say that the main problem of the pointers and references, because they are more or less the same, it is that they do not express the ownership. But we can think about an object which implements the right technique and allow to express the ownership of a resource. And let's try to look at a very small implementation. It's a very trivial implementation of an owning pointer. Okay. The owning pointer has a default constructor, which is explicitly like default. So it will just initialize the class invariant with the pointer, the private member pointer at line 25 with null pointer. And then we have at line 5 another constructor that takes in a pointer of the type. We have also seen templates, so we can understand this part of the code. So of a pointer of type T that gets copied inside the, oh yeah, I think I can. Oh, is it better now? Okay. Okay, so the owning pointer, we were talking about let's say the custom constructor that takes in a row pointer to the resource, and it just copies it inside the private member, the only private member that this class have. Then we have the destructor that just cares about deallocating the resource with the delete, just if the pointer is a valid pointer. So if the pointer stored inside is not valid, so it's a null pointer, it won't, this class won't release anything because there is anything to release. While if it is set somehow, well, it is going to be released correctly. Then we have the pair of copy constructors. Well, the copy constructor and the assignment operator for the copy with the copy. and they are deleted. This means that this object is not copyable. We cannot have a copy of this object. Thinking about ownership, if we get the ownership of a resource, let's think about a very big memory allocation. If we want to define the semantic of such an object about copy, what does copy mean? Well, it may mean creating another allocation, another big allocation, and copy all the values. It doesn't really make sense in such a generic example. So it is not copyable. So we cannot have a duplicate of this object. But from line 15, we start defining the move semantic part of this object. So we can move the object. And as you can see, there is the swap between the pointer stored inside the class and the pointer stored in the class which we move from. And this is, let's say, we do the swap because we want to ensure that the object we move from, so the one where we steal the things, still will be in a, let's say, defined state. We will put the null pointer in the moved from object. In this way, we can say, okay, you don't have to release anymore the resource because now it's mine. And this is even more, let's say, evident in the assignment operator move constructor, because when we construct an object with the move constructor, the current object does not exist. We are building it. And from how we define this object, it starts with a null pointer. But with the assignment operator, we have two objects that may be both valid. And since we are stealing from RHS object to get all his internals and making them mine, before doing that, we have to deal with what we may have internally. So if we point to a resource, we have to manage it. And so you can see the difference at line 17. If the pointer currently is valid, we have to release the resource. And we also set a null pointer because it's the class invariant that we impose on our class. And then we do exactly the same thing we did for the move constructor. So this is a trivial implementation. There are maybe some part that may not be so straightforward or, let's say, clear to understand at first sight, but it is a very basic thing. We can just realize one of the major problems of this implementation. I don't know if anyone realized any problem about this. We may have to, let's see if someone can see what's the main limitation of this class. We can say that it does not allocate, so it gets an allocation from the user that passes in a pointer, and at that point, the class becomes responsible, so it gets the ownership of the resource. But there is a problem, and it's on line 9. I don't know if anyone can propose any, I'm not saying any change, but what the problem, what may be? Exactly so. It cannot delete arrays. It cannot delete the arrays, and it's even more, it's assuming that what the user passes is an allocated value. So if it passes an allocated array, an array on the heap, it won't work. So it is quite restricting this implementation. But the good news, let me switch back to the slideshow. Oops. Okay. We don't have to do it because luckily the STL provides us already these helpers. We have in the memory header, we have the unique pointer, which is not exactly, and I'm not going to say exactly, but it is the correct version of what we've just seen with the owning pointer. So it represents the unique or exclusive ownership. Then it provides also shared pointer and weak pointer. Both they are shared ownership, so they have the machinery we were talking about previously, and we are going to see it in the next slides. And they are already there just to be used, and they are really powerful. And these are called also smart pointers. I don't really know why they are smart, but yes, they are more powerful in terms of semantic of representation in the code because they express ownership of the thing. It's not just like raw pointers that do not express any kind of ownership. I reported here from C++ reference, which is a site that you should really use when you have to work with C++. This is the, let's say, I screenshot just a part of the reference about standard unique pointers. And what I want to highlight here is, well, we have some modifiers. You can see the release, the reset, and the swap. The release just returns a pointer to the manage object and releases the ownership. Releases the ownership. So it doesn't release the actual resource. It doesn't delete the memory. It releases the ownership to the caller. The reset replaces the managed object. And then the swap, it's a utility that we used to have with this kind of data structures. Then I want to highlight that there are observers like the get, which returns a pointer to the managed object, but differently from the release, it doesn't release the ownership. The ownership is still of the unique pointer. Can you see the difference? Okay, because the main point is about the ownership. The release gives you a pointer, but the unique pointer is not the owner anymore of the resource, while the get gives you access to the resource, but you still have the ownership inside the unique pointer. So you have to you can still play with the ownership, but using the unique pointer. Then I want also to highlight just one small thing that, well, there is the last two sections of this screenshot are single object version and array version. As we pointed out before in the trivial implementation that was suffering of the problem of not dealing with arrays, if you look at the single object version, it reports like unique pointer angle brackets t, while the array version, it is reported as unique pointer type square brackets. So unique pointer implementation deals with the arrays. If you pass in a resource, which is a single value allocated on the heap, it will be a simple, it will just release the resource with a simple delete. But if you pass in an array allocated on the heap, it is able to understand it because through template programming, it is possible to deduce the different cases with template specialization. it will manage also the array. So it will do the delete array on destruction. And very last thing to point out here, this unique pointer works exactly as a row pointer in terms of usage. Because if you look at the last two sections, there is the implementation of the operator star and operator arrow that can be applied to a unique pointer just as a normal smart pointer. And when you apply these two operators to a unique pointer, you exactly work like if it was a row pointer. Then there is also the plus operator brackets, square brackets to access an array like a row pointer. Okay, then there is the shared pointer. The API is more or less the same. Here, I just want to highlight one thing. There is the useCount function, which returns the number of shared pointer objects referring to the same managed object. As we said before, the shared pointer is shared ownership. So there is no a single owner, but we may have more depending on a lot of things. When the point of the program, it depends at runtime. And we can know how many user we have, how many owner through that shared pointer we have by using useCount. Okay, about shared pointer, we are at the point where we want to understand the machinery behind the shared pointer. Previously, in our implementation, we said that we didn't implement the copy constructor and the related assignment operator for the copy because we didn't want to make the copy available to the user because it doesn't make sense. It didn't make sense. But for the shared pointer, the copyability allows to extend the ownership. Copying a shared pointer means sharing the ownership. Means that we get another object that points to the same resource, exactly the same resource, but the group of owners is extended by one, which is the new object. And let's say the shared pointers are also known as reference counted smart pointers. And this alias exposes how they are implemented, and we are going to see why and how. As we said before, for unique pointer, it was enough the language, but for the shared pointer, there is a machinery behind. I think that it is not really viewable, this snippet here, but just to report what it is written there, there is a pointer to resource, as a row pointer to the resource, and there is a counter that I called community, but it's just a counter of how many shared pointers there are, how many users of this resource there are. And this control block is part of the machinery, and it is the one that points to the resource and which is shared among the different owners that I represented here with an AND. Here we have 3 shared pointers copies that are pointing internally to the control block, and the control block internally points to the resource. How does it work? Well, the control block is what allows to not release ahead of time the resource, because the resource can be released just when there are no more users. Okay. If there is just one shared pointer, the resource cannot be released. If there are 2, who has to decide which one to release? Well, when the first one cannot release as soon as it finishes to use it, because there is still the other one playing with the resource. And so also here, the ownership is quite clear. As far as we know that there is an owner somewhere, so on the left, these hands, as soon as there is at least one, we cannot release the resource. The main point about shared pointers, about, let's say, the downsides, is that they requires two heap allocations, because we have to allocate the control block and the resource itself. And so it is suggested to use make shared, which at least allocates both all at once. So it's just a memory. There will be two separate parts of the memory, but it is just a memo lock, just one time. And what it is worth highlighting about shared pointers, it is that the control block is shared by different users, by different shared pointers. And the control block has to be thread safe, because the shared pointer is thread safe. But this doesn't mean that the resource is thread safe. Just the control block is thread safe. This is necessary because if we have, let's say in this case, three shared pointers, the three hands on the left, if they access the control block at the same time to update the community counter, saying, I want to take me out from this ownership, the community has to be updated atomically, because if the update comes from different threads, it may be problematic. And so the control block, which is implemented using atomic, requires comes at a cost. It has synchronization, so it is costly, but it is thread safe. But again, the control block is thread safe, not the resource. If we access the resource from different threads through a shared pointer, we may end up with race condition. We will end up in race condition if we write on the same resource. Okay, just some quick, let's say, extra about smart pointers. There are some helper functions which are make unique and make shared that allows you to allocate the memory without using the new. And it is generally suggested to not have any new and delete in the code. So with make unique, you can have also this, let's say, helper. And in general, if you're not sure about the ownership, use unique pointer, because you can always move from unique to shared, but you cannot do the opposite. So if in your, let's say in your library, you want to return a resource by expliciting that this resource has to be owned by the user because it is given as an object with ownership, and you're not sure about the ownership, if it will be unique or it will be shared, just return it as unique. The user, in case, can convert it to shared by just moving in the unique to the shared pointer. And at that point, the resource becomes shared, and the user knows that he has to deal accordingly, because if he wants to share it with different threads, he has to manage also the race conditions. Okay, generally there is this opposition between raw and smart pointers, but it is not the case. It is raw plus smart pointers. When you write code, you don't have to think about, if I'm starting using smart pointers, I will always use smart pointers, because smart pointers are not a one solution for all, because raw pointers are still very useful. And the main point to keep in mind when you write code is, if I want to express ownership when I write the code, with raw pointers, you're expressing that you don't want to deal with the ownership, and we will see an example quickly. While with smart pointers, you're saying, I want to give the ownership or to give the ownership to a part of the code. So you're clearly expressing something via your API. It's very important also from a readability and maintainability point of view of the code. It's not just about correctness. Let's see one example about, well, I try to depict a nested function calls. The external function named function gets in a shared pointer that it passes through some nested calls, and it arrives to the deepest one, which is nested op, that still takes the shared pointer. Well, in this code, just from a let's say from a semantic point of view, the function from the outside takes the ownership of the pointer, and then it passes the ownership to the call one, and then it passes to the call two, and then it passes the ownership again to the operator itself. Can you figure out what is the main problem of this, let's say, code, which is not a code, but this call tree? Can someone say what is the main problem here? Oops. The function, let's see it from a timeline point of view. The function assures that the shared pointer that it gets in, ownership in different scopes, yes. Yes, you're on the right track. Is it really necessary to express the ownership at all the nested calls? I mean, once the function, the outside one, keeps the ownership, the function is responsible for the object that it is pointed by the shared pointer. And then all the nested functions are in the lifetime scope of the function. They don't really care about the ownership, right? So we can just switch to using row pointers. And this is not just about, let's say, just because we want to use row pointers, because this thing has implications also on the performances it may have. At least it is more costly to use this one with respect to this one. Does someone have any idea about why this version with shared pointers in all the calls is more expensive than the one with row pointers? You have to copy the pointers. Yes, the smart pointers. And what exactly, Olivier? Yeah, increments and decrements for each level, which is what Sol probably was saying, because you have to copy the smart pointers. And by copying the smart pointers, you have the atomic operation. Yes, exactly. Because you have to deal with the ownership, and the ownership with the shared pointer means playing with the control block, and the control block being thread safe as a cost, a synchronization cost. Okay. Now, some guideline that I want to point out. We already, let's say, talked about them more or less. These guidelines are available. I reported the source here, are available online, and I suggest you to give a look at them. And when you have some doubt about what should I do, what it is better, I suggest to give a look at there, because they are quite good. And here I reported just the ones about resource management. And in green, the first one, R1, manage resources automatically using resource handles and dry. Well, it is something that Mauro already mentioned yesterday. Today, we talked about the R3 and R4. A row pointer or reference is non-owning. So we now know that what ownership means. And we know that row pointers and row references are non-owning. It doesn't mean they don't have to be used anymore. It means that they do not express ownership. Then we have R10 and R11, the red ones. We more or less said that when we presented the helper function, make unique and make shared. Through them, you can avoid calling this new delete malloc free explicitly. And then there is also a section always in the resource management about smart pointers. Again, the R20 unique pointer or shared pointer represents ownership. Prefer unique pointer over shared pointer unless you need to share ownership. We also said that. Use make shared, use make unique. If you go on the site, you can see also, let's say, from time to time, you can find examples about it. So they are also, there is a small description about why, but this is something we already cared about. Now there are a part about passing pointers, and here are given some advices about how you should pass pointers. And mainly, it is about if you want to explicitly express lifetime semantic, okay, use smart pointers. And pass these smart pointers as reference just if you want to change the unique point, the smart pointer itself. Anyway, I will suggest to give a look at these guidelines. I will share the link maybe after the presentation, so you can give it a look, and we can also talk about it in the Q&A session or the hands-on. I don't know, but I suggest you to give a look at this site, and in case we can exchange some view about it. The last thing about, let's say, about the guidelines, about passing parameters, I want to share with you is this slide that I took always from the same site we used before. Thanks, Mauro. And these are the general guidelines. This is the normal version. There is also an advanced one. But these are the guidelines about returning parameters, returning values and passing parameters. And you should just stick to this table. You don't have to think too much about how to pass parameters, because the compiler with copy elision and return value optimization, for example, gives you all the optimization that you can have to get just to have this returning by value work in every case as maximum, and you can get just the best performance ever. As you can see, there is just one case for the out parameter. Okay, if it is an out parameter and it is expensive to move, because here we have an array of a big structure. So the move means copying the internal structures from one side to another, or at least moving them. But it is expensive to move. It suggests to use returning by reference because we don't have to move it. But in all other cases, just use return by value. And if you have in-out parameters, just use reference in every case. The difference you get is when you have an in parameter, and if it is very cheap to copy, like Mauro yesterday said about int, it is not worth passing it by constref and int, because it is more or less the same cost of passing it by value. And so if they are very cheap to copy or impossible, like unique pointers, pass it by value. In all other cases, pass it by constref, because if you want to retain something that you pass, for example, if we are here in the f function and inside the function we want to extend the ownership, inside our code, inside the function, we can do it optionally, because if we pass by value, for example, a small pointer, at the calling point, we get the ownership shared. So we get the ownership there. While if we get a const xref, it is not mandatory. If in the function we have some logic for which, well, we have we don't have to do anything, so we don't want to get the ownership of the past value. Okay, we don't do anything, and the constref is pretty cheap because it's just a pointer. But if we want to copy it inside, we can do it. We can just copy it inside the function just whenever it is worth it. And at the first sight, this table is not very straightforward. There are a lot of implication in all these choices. And I suggest you to give a look at this video on YouTube. And it is already set on the right time point. It is very interesting to see the main reasons why these guidelines are taken as standard good guidelines, and they are good more or less always. There is also an advanced version of this slide, which allows you to, it is an extension that allows you to access more advanced passing parameters option, but they are very specific, and generally you don't have to apply them. They are for very specific use cases, when you can do something very smart in the move for an object. But just stick to these ones, and you will do the right thing.